You probably know about the perfect numbers. 6, 28, 496, and so on are the only numbers with the property of equaling the sum of their factors. Perfect numbers are extremely rare, with only 51 known and gradual progress towards finding new ones. But if we relax their requirements slightly, we can find a whole world of almost perfect numbers, which are just as much, if not more beautiful than the perfect numbers. In this video, we'll look at the many ways in which a number can be almost perfect, which will ultimately uncover some deep mathematical truths. Before that, we need some background, but if you already know all this, feel free to skip to the Descartes number. So every number has a list of factors that it's divisible by. The ones other than n itself are called its proper divisors. If you add them up, you get something called that number's aliquot sum, denoted S of n. In the last video, we saw how it's used to characterize numbers' personalities, but perfect numbers are by far its most famous application. Perfect numbers are those where S of n equals n, and they've been known about for thousands of years. One reason for their popularity is mathematical beauty. Since numbers are composed of their factors, perfect numbers equal the sum of their parts. Additionally, the sum of proper reciprocals of divisors always equals exactly 1, which makes them feel perfectly complete, hence the name. Another reason for their popularity is their mysterious and unsolved nature. It's unsolved whether there are infinitely many, and the search for new ones comes in two forms, even or odd. We'll start with even. By the Euclid-Euler theorem, we know every even perfect number has a corresponding Mersenne prime, and vice versa. A Mersenne prime is just a prime number 1 less than the power of 2, and it's unknown if there are infinitely many, but it does seem pretty likely. They're found by the GIMPS project, and every new one discovered comes with a new even perfect number. Odd perfect numbers are much more elusive. It's not proven that they can't exist, but not a single one has ever been found. The closest we've come is 198,585,576,189, which is known as the Descartes number. This is the first type of almost perfect number, and that's because it tricks you into thinking it is perfect. You see, the way we check if a number is perfect involves something called the sigma function. It's the sum of divisors of n including n, so sigma of n equals s of n plus n, and perfect numbers have sigma of n equals 2n. Sigma is a multiplicative function, which means if a and b are co-prime, then sigma of a times b equals sigma of a times sigma of b. This makes it easy to calculate because you can always split up a number using the prime factorization. For example, the prime factorization of 360 is 2 cubed times 3 squared times 5, so sigma of 360 equals sigma of 2 cubed times sigma of 3 squared times sigma of 5. Sigma is really easy to calculate when n is a prime or a prime power using a geometric series identity. Therefore, we have a relatively simple procedure to find the sigma of any number. Just take the prime factorization, find each sigma value using the identity, and finally multiply all those values. When applying this to the Descartes number, you'll first factor out all the 3's, then all the 7's, 11's, and 13's, at which point you're left with 22,021. After applying the identity on these 5 terms and then taking the product, you end up with exactly double the Descartes number, which would make it an odd perfect number. But there's just one problem though. That identity only works for prime powers, and as it turns out, we didn't actually finish the prime factorization. 22,021 is not prime, it's actually 19 squared times 61. With the full prime factorization, you'll find the true sigma value is a bit more than double the Descartes number, making it abundant rather than perfect. The way it's usually described is that it would be an odd perfect number if only 22,021 were prime. But the only way 22,021 could be prime is if its prime factors 19 and 61, along with all multiples of them, cease to exist, except for 22,021 and all multiples of that. So I prefer to describe it as a perfect number if you use the procedure but don't finish the prime factorization. We can find more numbers with this property by defining it mathematically. For a number n, we can say that the incomplete factorization includes a bunch of prime powers and then a fake prime b. If a is the product of those prime powers, then n equals a times b, and under the incorrect assumption that b is prime, we would have sigma of n equals sigma of a times b plus 1. A perfect number would have sigma of n equals 2n, which in this case is 2ab. So we want to find when 2ab equals sigma of a times b plus 1. After some algebra, we could see that when sigma of a over 2a minus sigma of a is a positive integer, you can use b as a fake prime to get a Descartes number equivalent. So I made a program to find these, and they're actually quite common. They feature a lot of numbers 1 less than a power of 2, and this actually relates to Mersenne primes. For example, 511 isn't prime, but if it were prime, it would be a Mersenne prime due to being 2 to the 9 minus 1. And by the Euclid-Euler theorem, Mersenne primes always have corresponding perfect numbers, and so these fake Mersenne primes always have corresponding Descartes number equivalents. Not all of them are like this though. My favorite example is 924. It equals 2 squared times 11 times 21. If you take 21 as a fake prime, then 924 would be perfect. But just like all the examples I found, it's even, and we already know that the even perfect numbers must correspond to Mersenne primes. That's why the definition for a Descartes number specifies it must be odd, and in this case, the previously mentioned one is the only known example. For the next type of almost perfect number, we have to go back to the definition. It requires a number to equal its Aliquot sum, which is the sum of divisors excluding n itself. But why is n excluded? Well, there are kind of multiple reasons, but my main reason is that if you include it, the sum is heavily impacted by the size of n and gives less insight into its factors. That's because any number n is automatically divisible by itself, making it a trivial divisor. But there's another trivial divisor every number has, which is 1. So in my opinion, it makes sense to also exclude 1, in which case you're taking the sum of non-trivial divisors, which is just the Aliquot sum minus 1. So that raises the question, what numbers equal their sum of non-trivial divisors? Well, these ones are called quasi-perfect numbers, but unfortunately, not a single one has ever been found, odd or even. Just like odd perfect numbers, it's not proven that they can't exist, we just haven't found any. But we do know some requirements that a hypothetical quasi-perfect number would meet. Basically, it must be an odd square. This means if you write out the prime factorization, then the exponent above the 2 must be 0, and the remaining exponents must be even. It's actually pretty simple to prove the second half of this. A quasi-perfect number has an Aliquot sum 1 greater than itself, so if n is odd, s of n must be even, and vice versa. Since an even plus odd is always odd, we know sigma of n, which is n plus s of n, is odd. And since sigma of n is multiplicative, it will only be odd if all the sigma values of the prime powers are odd. Sigma of 2 to the k is always odd, but for other primes, the parity is simply the opposite of the exponent. So the only way to get an odd sigma of n is if all the exponents besides 2's are even. Anyway, quasi-perfect numbers were first examined in an Italian paper, in which they were called quasi-perfetti. Quasi is just the Italian word for almost, but when bringing the term into English, the quasi part isn't translated. Instead, that term has a different meaning, because our next type of almost perfect numbers have the official name almost perfect. Just as a quasi-perfect number has s of n equals n plus 1, an almost perfect number has s of n equals n minus 1. Unlike last time, we actually have examples of these. So what are these numbers that get the distinction of being officially called almost perfect? Well, they include 1, 2, 4, 8, 16, and so on. That's right, every power of 2 is an almost perfect number. And it's easy to see why just using the geometric series formula. These are actually the only known almost perfect numbers, but it's not proven that others can't exist. The focus is mainly on finding an odd almost perfect number other than 1. If we ever do find an odd almost perfect number n, it will automatically give us another Descartes number in the form of n times 2n minus 1. That's because we know n and 2n minus 1 are coprime, so when you take the sigma of the product, you can split it up. Sigma of n is 2n minus 1 due to it being almost perfect. Meanwhile, if we take 2n minus 1 as a fake prime, then its sigma value is 2n. So in total, sigma of n times 2n minus 1 is 2n times 2n minus 1, which is exactly double its own value. Almost perfect and quasi-perfect numbers are easy to visualize when we graph the function s of n versus n. Just like how perfect numbers fall on the line s of n equals n, quasi-perfect and almost perfect numbers fall on the line 1 unit above or below respectively. But since the function only inputs and outputs integers, there's an alternate visualization we can use to find more types of almost perfect numbers. We'll start by drawing a 1 and then repeat the following process. add the next available integer to the diagram, and then draw an arrow pointing from it to its aliquot sum. So 2 points to 1, just like all primes, 3 points to 1, 4 points to 3, 5 points to 1, 6 points to itself because it's perfect, 7 points to 1, 8 points to 7, and so on. Eventually, we get the first abundant number, 12, whose aliquot sum 16 is not yet on the diagram. So we'll just add it now, take care of its arrow as well, and then skip it later. We actually have to do the same thing with 15, but then we get 9, and we can resume with 13 and 14. You can keep going as long as you want, and this is what it looks like up to 137. You can start at any number and keep following the arrows to get something called the aliquot sequence of that number. As you can see, the vast majority of them eventually reach a prime, which then points to 1, and then 0, where the aliquot sum isn't really defined, so the sequence terminates. Some numbers take a while to get there, for example 120, whose aliquot sequence has 12 steps before hitting the prime number 12,161. But not all aliquot sequences terminate, and in fact there are 5 different ways in which it might not terminate. The first two can be seen immediately on the diagram. Perfect numbers equal their aliquot sum and therefore point to themselves, forming an infinite loop instead of stopping at 1. These loops can also function as alternative destinations. Numbers whose aliquot sequence ultimately leads to a perfect number rather than a prime are called aspiring, and the first few are 25, 95, and 119. You can also get infinite loops with multiple terms. If you have a cycle of length 2, it means the two numbers equal each other's aliquot sum. Pairs of numbers like this are called amicable. They're actually way more common than perfect numbers, with over 1 billion known pairs, the first being 220 and 284. If you have a cycle with length greater than 2, the numbers are called sociable. There are 5,398 known 4 cycles, but other cycle lengths are extremely rare. We only know of 5 6 cycles, 4 8 cycles, and only 1 cycle each for lengths 5, 9, and 28. The remaining ones, including length 3, don't have any known cycles. Now, just like perfect numbers, amicable and sociable cycles can serve as alternative destinations, and some aliquot sequences end at one of these instead of terminating at 0. These numbers don't have an official name, so I'm going to call them socially aspiring. The fifth way in which an aliquot sequence might not terminate is the most interesting of all, because it may or may not even exist. Going back to the diagram, you may have noticed I stopped at the strangely specific 137. That's because the next number, 138, goes on quite the adventure. It gets all the way up to 179 billion before eventually coming back down and finally hitting a prime at step 176. But what if a number's aliquot sequence never did come back down and just diverged to infinity? Is that even possible? That question remains unsolved, but we do have a candidate sequence, being that of 276. My program uses 64-bit integers, so it stops working after 4.9 quintillion, but the sequence has been calculated further, and it just keeps going. After about 2,000 steps, it reaches numbers so big that they haven't been factored yet, which is a necessary step to calculate the aliquot sum. So for now, the ultimate fate of 276 and the other numbers in its sequence remains a mystery. One thing you might be wondering is how such a sequence could possibly exist. About 3/4 of numbers are deficient, so if it's effectively random which one the next term will be, then you wouldn't expect so many abundant numbers in a row. But the thing is, in the aliquot sequence, it's not random. As mentioned earlier, sigma of n can only be odd if all the sigma values of the prime powers are odd, which is pretty unlikely, so sigma of n is usually even. This means if n is even, s of n will usually be even too. A similar thing applies with 3. If even a single one of them is divisible by 3, sigma of n will be 2, so if n is a multiple of 3, s of n usually is 2. Combining these means it's pretty easy to get multiples of 6, whose aliquot sum is another multiple of 6. Being divisible by 6 already guarantees a number is abundant, so s of n can just keep going up and up. But if it does escape the multiples of 6, it's still possible to rise, but usually it goes back down. Now you might remember from earlier in the video, a quasi-perfect number equals its sum of non-trivial divisors rather than proper divisors. For that reason, I'm going to call it the quasi-aliquot sum. Even though there aren't any known quasi-perfect numbers, we can still make use of the quasi-aliquot sum in other ways. Specifically, we can construct a diagram analogous to the one with aliquot sequences to find quasi-aliquot sequences. All of the concepts carry over, and you can just add quasi before the name. There may not be any known quasi-perfect numbers, but there are plenty of quasi-amicable numbers, of which the first pair is 48 and 75. But the thing I find most interesting is that we don't get any of those crazy long sequences. I had the computer look at the quasi-Aliquot sequences for all numbers up to 1,000,000, and not only did it never find a sequence longer than 50 steps, but the biggest number it encountered was only 6.1 million. So why is this the case? Well, with the Aliquot sequence, multiples of 6 usually lead to more multiples of 6 in an abundant cycle. But if you subtract 1 each time, this isn't the case, so it's much easier to get deficient numbers. Speaking of abundant and deficient numbers, my favorite way to measure how prime or composite a number is the relative abundance, which is sigma of n divided by n. Deficient numbers score less than 2, abundant numbers score greater than 2, and perfect numbers score exactly 2. But there are far more values of interest than just 2. In fact, we can find interesting results by looking at any positive integer value. In general, numbers whose relative abundance is a positive integer are called multi-perfect numbers. Perfect numbers are a subset of these, and some of the other types have specific names as well. The first subset is those with relative abundance 1. If you look at just primes, then sigma of n approaches 1 asymptotically but never reaches 1. That's because at the very least, every number has 1 and itself as factors, which already makes the relative abundance strictly greater than 1. The only number with relative abundance 1 is 1 itself, because if you look at the factors of 1, 1 is itself, so it only gets counted 1 time, and then you divide by 1 to find the relative abundance of 1 is 1. Next up are the triperfect numbers, the first of which is 120. If you add up the divisors, you get 360, which is exactly 3 times 120. And if you calculate sigma of n over n multiplicatively, you'll find that the denominators cancel out and you're left with an integer, 3. The next triperfect number is 672, and there are 4 more known after that. If we ever did find the elusive odd perfect number though, it would automatically give us another triperfect number in the form of 2n. That's because 2 and n have to be coprime, so sigma of 2n equals sigma of 2 times sigma of n. We know sigma of n equals 2n by the definition of perfect numbers, and sigma of 2 equals 3, so we end up with the sigma of 2n being 3 times 2n. So if an odd perfect number exists, then there are more than 6 triperfect numbers. By the contrapositive, if we can prove that there are only 6 triperfect numbers, that would mean odd perfect numbers don't exist. It's unproven, but it seems pretty likely that these 6 are the only ones. To see why, we need to look at the other multiperfect numbers. From the relative abundance graph, quadperfect numbers seem like they'd be even rarer than the triperfect numbers, but actually, there are 36 of them known. The smallest is 30,240, and the biggest has 46 digits. This is obviously a huge range, but in the grand scale, it's pretty small. To demonstrate this, we'll take the relative abundance graph, make the horizontal axis doubly logarithmic, and look at only multiperfect numbers. Once we zoom out, you can see the range of quadperfect numbers is not much bigger than the range of triperfect numbers. Multiperfect numbers actually continue to get more common with higher relative abundance, so we can continue this graph to show all the known multiperfect numbers. At this point, you can clearly see a pattern forming. This pattern goes up to 11, and the only reason it stops there is because we haven't checked numbers that big yet. But we have checked all candidates up to a certain point, so we know there aren't any multiperfect numbers in this triangle. So if there existed another triperfect number, it would have to be past this triangle, which seems unlikely considering how strong the pattern is. This is pretty convincing evidence that there are no more triperfect numbers, and therefore that odd perfect numbers don't exist. Anyway, enough about multiperfect numbers. Now it's time for hemi-perfect numbers. Instead of having integer relative abundance, they have half-integer relative abundance. 1/2 is impossible, so the first possibility is 3/2. We get a number like this right away in the form of 2, but never again, and we'll cover the reason for this a bit later. For now, we'll look at the next possibility, 5/2. The first number with relative abundance 5/2 is 24, whose sum of divisors 60 is 2.5 times 24. There are 2 more with this relative abundance, but that's it for 5/2. As for the rest of the hemi-perfect numbers, their distribution is pretty much exactly what you'd expect based on how they fit in with the multiperfect numbers. Now, just like perfect, weird, and multiperfect numbers other than 1, all the known hemi-perfect numbers are even. But unlike those other types, we actually know for sure that there can't be any odd ones. That's because the half-integer relative abundance is the reduced fraction of sigma of n over n, so n must be a multiple of 2 in order for division to reduce it to 2. Now these specific values of relative abundance, such as integers and half-integers, are known as relative abundance clubs. But we're not limited to integers and half-integers, and in fact we can come up with a club for any rational value. For example, 40 and 224 both have the same relative abundance, 9/4, so they're both in the 9/4 club. But there's also another member, 174,592. When numbers have the same relative abundance as each other, they're known as friendly numbers. On the contrary, if a number is part of a club on its own with no other members, it's known as solitary. One example is the Hemi perfect 2, whose relative abundance class 3 halves contains nothing other than 2 itself. But how do we know this? Well, there's a pretty simple condition. If n and sigma of n are coprime, then you will never get another number with the same relative abundance as n. If you could find one, it would mean there's an a where sigma of a over a equals sigma of n over n. Since they're coprime, sigma of n over n is an irreducible fraction. So for sigma of a over a to reduce to that, a would have to be a multiple of n, which we'll call k times n. If we multiply both sides by k times n, we end up with sigma of k times n equals k times sigma of n. Obviously k equals 1 works, but other than that, there are no solutions. To see why, consider the factors of n, which add up to sigma of n. If we multiply all of them by k, then these are all factors of k times n. But if k is greater than 1, then k times n has more factors than just these, because even at the very least, it also has 1 as a factor. So the sum of all the factors of k times n is greater than the sum of k times each factor of n. In other words, sigma of k times n is greater than k times sigma of n. This contradicts the previous statement that they're equal, so k cannot be anything other than 1. This means any number a with the same relative abundance as n must be of the form a equals k times n, where k is 1, meaning no other numbers have this relative abundance, making n solitary. This one rule gives us a lot of numbers that are known to be solitary. Additionally, some numbers don't have the coprime property, but are proven to be solitary in other ways. As for the other numbers, a lot of them are proven to be friendly due to being in clubs with other known members. But then there are numbers like 10. Its relative abundance is 9/5, and we haven't found any other numbers in this club, but we also haven't proven they can't exist. And it's not out of the question for friendly numbers to have huge gaps, as can be seen with 24's club of 5 halves. So 10 may or may not be solitary, and the same thing actually applies to a lot of numbers. That's it for relative abundance. The last main category of ways a number can be almost perfect is relatively simple. When adding up the proper divisors, abundant numbers always overshoot the mark of perfection. But all you have to do to hit perfection is only add some of the factors. So we say that a number is semi-perfect if it equals the sum of some subset of its proper divisors. But the thing is, semi-perfect numbers are extremely common. All abundant numbers other than the weird ones are semi-perfect, which makes them feel a lot less special. We can get around this by making the requirements more strict. My first idea was numbers that are one factor away from perfection. In other words, you can remove a single factor from the sum of proper divisors to make it equal n. These ones are called near-perfect numbers. One example is 196, where if you add up all its factors except for 7, you get 196. The reason this works is because the difference between n and its aliquot sum is itself a factor of n, meaning you can reconcile the difference in one move. So the near-perfect numbers can alternatively be defined as abundant numbers, where d equals s of n minus n is a proper divisor of n. So you can find these by checking abundant numbers for when n is divisible by s of n minus n. As it turns out, they're actually quite rare, with only 45 under a million. I noticed a few interesting patterns in them. First of all, there's a lot of primitive abundant numbers. That's because primitive abundant numbers are usually just barely above the abundance threshold, so it makes sense that they're only one factor away from perfection. Another pattern is multiples of perfect numbers, and in fact, the only number I found outside of these categories is 40. Now, obviously 45 out of a million is quite rare, but compared to perfect numbers, it's a lot, which makes them feel slightly less special. So what can we do to get a very rare type of almost perfect number? Well, one idea involves the sum of unitary proper divisors. But what is a unitary divisor? The definition is that a divisor d of n is unitary if d and n over d are coprime. But the best way to think of it is with the prime factorization. When finding factors of n, you can change the exponents above the primes, where each one can range from 0 to its original value, resulting in a multidimensional table of factors. But to be a unitary factor, the exponent can be 0 or its original value, but nothing in between, so you only get the corners of this table. So basically you could take all of that prime or none of that prime. The sum of unitary divisors is denoted sigma asterisk of n, and as for the sum of unitary proper divisors, I'm going to call it the unitary Aliquot sum and denote it s asterisk of n. With 36, for example, it has 9 factors, but only 4 of them are unitary, and only 3 of those are proper divisors. So its unitary Aliquot sum, 14, is much lower than its regular Aliquot sum, 55. The same thing applies to a lot of numbers, and the unitary requirement basically gives a nerf to any number with a lot of the same prime factor. But we do still consistently get numbers with s of n greater than n, for example numbers 6 away from a multiple of 36. So that raises the question, are there any numbers that exactly equal their unitary Aliquot sum? Well, these are called unitary perfect numbers, and there are several of them known. The first is simply the perfect number 6, since its factors are all unitary anyway. But the next one is 60, which you can verify by adding the unitary proper divisors, or you can calculate it with the fact that sigma asterisk of n is also multiplicative. After that is 90, 87,360, and this 24-digit number, but that's it. They just seem to mysteriously stop, and we don't know if there are any past these 5. Lastly, some almost perfect numbers are a bit silly. For example, consider 12. It has 6 factors, which is of course the first perfect number. On its own, this isn't that special, but then you look at its sum of divisors. Sigma of 12 equals 28, which is the second perfect number. So we say a sublime number is one where both the number of divisors and sum of divisors are perfect. This definition was pretty much made for 12, and considering how rare perfect numbers are, it seems unlikely that it will ever happen again. But as it turns out, there's exactly one other known sublime number, and it has 76 digits. This seems like a freak accident, but if you look at the prime factorization, you'll notice an interesting pattern. It consists of 2 to the 126, and then 6 different Mersenne primes. When calculating sigma of n multiplicatively, the 2 to the 126 turns into a Mersenne prime, and the Mersenne primes turn into powers of 2. Eventually, you end up with 2 to the 127 minus 1 times 2 to the 126, which is the 12th perfect number. As for the number of factors, you have 127 choices for how many 2's to include, and 2 choices for each other factor, resulting in 127 times 2 to the 6th, which is the 4th perfect number, 8,128. The reason this works all has to do with 127. Not only is it a Mersenne prime, but it's also the exponent for another Mersenne prime. Its own exponent is 7, and if you subtract 1, you get 6. Then 127 minus 1 is 126, and 126 can be expressed as the sum of 6 smaller Mersenne exponents. Since they add up to 126, this guarantees the sum of divisors fits the form of an even perfect number. And since there's 6 of them, it guarantees the number of divisors fits this form. Of the 51 known Mersenne exponents, only 4 of them are themselves Mersenne primes, and of those, only 127 and the trivial case of 3 satisfy this very specific property. The sublime numbers really show why I like almost perfect numbers so much. It started by noticing a seemingly random anomaly, but ended with insight into Mersenne primes that are also Mersenne exponents. Since perfection is so hard to achieve, we inevitably find ourselves drawn to the search for aesthetic ways to get close to it. Not only are the results interesting in their own right, but they can also tell you more about the perfect numbers themselves, and get closer to solving their many mysteries. And the idea of solving a problem by closely examining generalized versions of it is a very important mathematical lesson. Those are all the almost perfect numbers for today. Let me know your favorite type in the comments, and if you learned something interesting, make sure to like and subscribe. Thank you for watching, and I'll see you next time. Bye!